In this part, let's try to understand what the linear programming is, and try to set up a linear programming model based on some simple setting. For linear programming, the basic thing you need to know is that is an optimization model. Optimization means either to maximize or to minimize an objective function. The keyword of linear programming is linear. It means not only that the objective function must be linear, but also all the constraints must be linear. To be more specific, a linear programming model is composed by three elements. A set of decision variables. They represent what the decision maker wants to control, or in other words, the decision he wants to make. An objective function. It means the goal that the decision maker wants to target. A set of constraints. They characterize all the restrictions that the decision maker must adhere to when making the decision. Let's play a single Lego game to see the typical problem setting for applying the linear programming. We will use Lego to make three different furnitures, table, chair, and lazy boys. Here is the product design. As you can see, to make a table, we need two large blocks for the top and two small ones for the legs. A chair needs one large block and two small blocks. Lazy boy is the most complicated one. Three large blocks for the bottom and the back, and two small ones for the arm supports. The profit margin for different furniture is different. Each table contributes $33, each chair $18, and each lazy boy $49. And what we are having is 8 large blocks and 8 small blocks. Those are the total materials we have to make the Lego furnitures. Then we need to decide, based on the available blocks, how can we plan our production so that we can make as much as possible money? I hope you can get some Legos, 8 large blocks and 8 small blocks, and play a little bit about these games and to see how many different furnitures you can make, and then calculate how much money you can make from that before you go into the next slides. Here is what I got. So I will make no table, and I will make 2 chairs and 2 lazy boys. Let's see how the blocks are utilized. So 2 chairs mean that we use 2 large blocks and 4 small blocks. And 2 lazy boys means 6 large blocks and 4 small ones. So you can see by this plan, we used up all the 8 large blocks and 8 small blocks. The corresponding profit can be calculated as $134. Something worth mentioning here is that we have not produced any table, though it has the much higher margin, $33, than the chair, which is only $18. Okay, from this result, it seems that more important thing is to fully utilize the resource instead of pure margin driven to produce the high profit products as many as possible. This Lego game is a typical linear programming type of problem. We have limited resources And by using these limited resources, we want to achieve a certain objective to maximize the total profit. So we can formulate Lego game into linear programming model by configure the three components we mentioned in the previous slides. First, we need to pick out decision variables. Obviously, that must be the number of the tables, number of the chairs, and the number of lazy boys we want to make. We will use capital T, capital C, and capital Z to represent them respectively. Second, we need an objective function constructed from decision variables that T, C, and Z. Our objective is to get highest possible profit. We know each furniture's profit margins, so times those margins to the corresponding decision variables, we get the profit function as the number of each different furniture. This is our objective function, and we want to make its value as big as possible by determining the value of T, C, and Z. Third, we need to configure the set of constraints. First of all, we have 8 large blocks. So our production plan cannot consume more than 8 large blocks. We know each table requires 2 large blocks, each chair 1, and each lazy boy 3. So we can calculate, based on different number of table, chair, and lazy boy, the total number of large blocks used, which must be no larger than 8. Similarly, we can set up the usage constraint for 8 small blocks. At the very end, there is an underlying default restriction. That is, for each furniture, we can either produce nothing or produce a few units. So T, C, and Z must be non-negative. From Lego game, we can now summarize the typical scenario for using a linear programming model. We must make sure the problem we are facing having 2 properties, deterministic and linearity. Deterministic means that everything is known with certainty. When making a decision, you will be sure the outcome, just like in the Lego game. Once you decide the number of the tables, chairs, and the lazy boys, you must know how many small and large blocks are used and how many profit is generated. Linearity is a more compound concept, which includes 3 aspects. The first one is actually the proportionality. Mathematically, it means a decision variable in the objective function or any constraint function is multiplied by some constant parameter. In the Lego game, the parameters in objective function are the unit margin for different products, and those in constraint functions are the block requirement for each product. All the parameters are constant, not depending on how many products you plan to produce. The second one is the additivity. So in the objective function or any constraint function, you can add or subtract the different decision variables, but cannot do any other computation among them, like multiplying different decision variables together or dividing different decision variables. In Lego game, we only add things together. The last one is also called divisible. So the decision variables are restricted to take the integer numbers. If the integer number makes more sense in problem setting, like in Lego game, we can first get the non-integer number optimal solution by assume there could be a fraction of furniture produced and sold. Then we round that non-integer solution to the integer one as our final decision outcome. Lego game is a typical example of product mix decision problem, which is one of important application of linear programming in operations and supply chain management. Besides that, we also can use linear programming to making inventory planning, make a profit navigation, decide the location of plants and facilities, schedule employees, machines, etc. Even when going out of the scope of operations and supply chain management, linear programming also has a lot of application. For instance, the one listed here, how to make a spending plan to get the largest utility. Or something like the study plan for using the time most efficiently.